I'd now like to go ahead and prove a couple things about ideals. These are things that are both useful and also give kind of some insight on kind of the nature of ideals. So in order to save time, I already have them written out here. So here's the first one. Basically says if you have a ring with unity and some ideal of that ring contains your multiplicative identity, then the ideal must be the entire ring. So it's a pretty easy proof. We're basically just going to do, since we're trying to prove set equality, we're just going to do a subset proof. Just from what's given to us here, we already know that J, sorry, that's a bad J. J is a subset of R. That's given. What we need is the reverse inclusion, that R is a subset of J. So to prove that, we're going to pick something in R. Say, let's say let X be an element of R. And we want to show that X is in J. Well, we're given that this is a ring with unity. So we could write X as X times 1. Just from the kind of the definition of our unity element. Multiplying by 1 doesn't really change anything. But now we're also given that 1 is in J. And since J is an ideal, multiplying anything by an element of J is still going to be an element of J. So here we have, here is our element of J, and we have a multiplication here. So this product, since it's an ideal, this product is going to be an element of J. And that's basically it. I mean, that says we picked an element in R, and now it's in J. So we get R is a subset of J. And now since we have both set inclusions, this implies that R equals J. Pretty easy proof. Easy, and yet it's actually pretty useful. We're going to use this in one of the next proofs that we're going to do. So let's go on to the next one. This next proof doesn't really have too much to do with ideals, but I'm going to need it for the next proof that we do, and it's also kind of insightful and enlightening. So it basically says in any ring you can't have an element that's both a unit and a zero divisor. So let's see why this is. Let's try to prove this by contradiction. So let's say an element, say X. X is both a unit and a zero divisor. Well, since it's a unit, we could say there exists an X inverse in our ring, let's call it R, such that X times X inverse is equal to 1. Okay, so then also, since it's a zero divisor, we could say that there exists a Y in R such that, say, X times Y equals 0. Now, this ring, we haven't assumed this is a commutative ring, so I mean, it could be Y times X. I mean, we could make a distinction between left zero divisors and right zero divisors, or maybe this particular element X is both a left and a right zero divisor, but it turns out for this particular proof it doesn't really matter, and you'll see why in a second here. So there exists a Y in R such that X times Y is 0 and Y is not 0. Okay, so we just have definition of a unit and definition of a zero divisor. So let's see where this can get us. Let's take a look at the expression X, actually I think we want X inverse X, Y. So now if we look at the right side of this part, from the second line here, this is X inverse times 0 from this, which is just 0, because anything times 0 is 0. But now if we look at the right side, this part, since this is x times its inverse from this first line, I guess I should say this is also technically x inverse times x. So from this first line we get this is also equal to 1 times y. And anything times 1 is just itself, so this just gives us y. But now since these are both equal to this, we get that y is equal to 0. So let me write that down. So this implies that y equals 0, which is a contradiction to what we said right there. So this particular element that we started with, this x, couldn't possibly have existed in the first place. So no element can be both a unit and a zero divisor. Alright, so let's move on to our third and final result of this video. These two first proofs that I just did they're kind of useful, and they're useful in certain situations, but I really only did them because they're leading up to this third proof. So let's see what this is here. It says if we have a commutative ring with unity, then that ring will be a field if and only if it has no non-trivial ideals. And the non-trivial ideals would be the trivial ideals would be the zero ideal and the ring itself. So I'll write these down. So the trivial ideals are just the set containing 0, and the ring itself R. So it'll be a field if the only ideals we have are these two. So this proof is a tiny bit more involved. This is an if and only if proof. Let's start with the backwards direction first. So we're going to do the backwards implication. So we're going to assume that our ring that we're looking at, this commutative ring with unity, has no non-trivial ideals, and we want to prove that it's a field. So what do we even need to show here? If we remember back to our definition of a field, we said a field is a commutative ring with unity, has no zero divisors, and every non-zero element is a unit. So what we need to show, we already have that it's a commutative ring with unity. So that part we're good. So zero divisors and every non-zero element is a unit. Well, from the last proof we just did, if we could show that every non-zero element is a unit, well, we can't have an element that's both a zero divisor and a unit. So if every element is a unit, then it couldn't possibly be that we have any zero divisors. So what I'm saying is we really only need to show that we have every non-zero element is a unit. So let's go ahead and do that. So let's say we have let x be a non-zero element. So x is in R, take away the set 0. So x is some non-zero element in our ring. And we just need to show that x has a multiplicative inverse. So let's take a look at the ideal generated by x. And I did this in the last video. I just forgot to tell you the notation for it. This is the set that we did. X times everything in R, such that R is in R. So it's just R times the x times the ring. And this is actually called a principal ideal, the principal ideal generated by x. So let's take a look at the possibilities that this set could possibly be. Remember, we're assuming that we have no non-trivial ideals. So either the ideal generated by this x is either 0 or it's R, the entire ring. Well, we've assumed that x is not 0. We also know that we have a unity element. So we could choose this R here to be 1. So we could say x times 1 is an element of this, or just x. And x is not 0. So this ideal contains a non-zero element. Well, that automatically right there eliminates the possibility that it's the 0 ideal. So if it's not the zero ideal, then it must be the entire ring. So this must be R. Well, if it's equal to R, then what that says is that every element of R can be represented by something of this form, as something times X. So in other words, in particular, our unity element, our 1, can be represented as X times some element, say Y. It would be a non-zero element since 1 is not equal to 0. And also, since this is a commutative ring, we could also write this as Y times X, which is the definition of a multiplicative inverse. We have something times X gives us 1. So Y would be the multiplicative inverse of X, and X would be a unit. And then since it's a unit, it can't be a zero divisor. And also, since it's arbitrary, that means that every element of our ring, every non-zero element, is a unit or has a multiplicative inverse. And that makes R a field. So that's our first direction. So let's go on to the forward direction now. Forward implication. So now we are assuming that R is a field, and we want to show that its only ideals are 0 and R. Alright, so to prove this, let's say that we have some arbitrary ideal of our ring. Let's call it I. We usually use I for ideals since ideal starts with I. I don't know if I've used this notation yet, but I think the notation that's somewhat commonly used is a triangle. So I is an ideal of R. That's what that means right there. And let's also assume that it's not the zero ideal, because if it's the zero ideal, then we're done. So I is an ideal of R, and I is not the zero ideal, not the set containing 0. And what we want to show now is if it's not the zero ideal, then it has to be the overall ring as a whole. So we want to show that I equals R. Alright, so if it's not the zero ideal, then it must contain some non-zero element. So we could say there exists an X in I such that X is not 0. Since it's not the zero ideal, it contains some element that is not 0. Alright, so now if we're assuming that R is a field, then since this is a non-zero element, then we have, we could say there exists an X inverse in R. It may not be in I, but at the very least it's in R, since R is a field. So there exists an X inverse in R such that X times X inverse is equal to, I don't know if we'll need both of them, but we'll say X inverse times X, and that's equal to 1. Okay. Alright, so let's take a look at this. We have X is in I. We said that right here. And I is an ideal. So here we have a multiplication. Let me switch colors. Here we have a multiplication of something with X. So since I is an ideal and X is in I, then this product is going to be in X, or in I. But this product is equal to 1. And so we have that 1 is an element of I. And by the first proof that we did in this video, we now can say that since we have an ideal that contains our unity, our multiplicative identity element, then we must have that I equals our entire ring, R. And that's what we wanted to show. If it's not the zero ideal, then it must be the entire ring. So that's our forwards direction now. So that completes the proof here. Alright, so now I'd like to talk briefly about the kind of the implications of this result that we just proved here. So what are the fields that we've talked about so far? We have the rational numbers, we have the real numbers, we have the complex numbers, and we also have things like z sub p for a prime, for p a prime. And I think that's all that we've talked about so far. So this result says that if these are all fields, then they have no non-trivial ideals. So that's actually kind of useful. If there's no non-trivial ideals, then well, first of all, there's no ideals to talk about, and second of all, there's not really any factor rings that we can really form out of any of these, since they're fields. So another way to say that would be, in terms of ideals and factor rings, fields are kind of boring. There's nothing really you can do with them. I mean, so say we have, let me get a good color. Say we have, if f is a field, the only two ideals we can talk about are 0 and the field itself. So the only factor rings we can form are f mod 0 ideal, which would just be f itself. I mean, you're just, if the ideal contains just 0, then this factor ring is just going to be isomorphic to your field yet. We haven't talked about isomorphisms yet, but we're getting there slowly but surely. And the other field you could, or the other factor ring you could talk about is f mod f, which would just be the 0 ring. So if you want to talk about factor rings, you kind of have to stay away from fields because they're not really all that interesting. The other thing I wanted to say was the fact that this is a commutative ring, that this is our hypothesis here that this is a commutative ring is very important. You can, for example, you can have a ring with unity that has no non-trivial ideals, but it's not a field because it's not commutative. One example that comes to mind is with matrices. You can have a ring of matrices that has no non-trivial ideals, but that doesn't make it a field because it's not commutative. So just watch out for that. And I think that's going to be it for this video, so I will see you in the next one.